Okay, so here it talks about the energy stored in an electric field or in the capacitor. So yeah, so here it says this is the total energy. Total energy will be du integration of du, and then it's actually mentioned that u here is u equals q times v, and here it try to starting from zero. Initially there is no charge in the capacitor, and then it tries to place a small charge 1 by 1 dq 1 by 1 negative dq on the other plate, 1 by 1 starting from 0 to up to q, and then placing q 1 by 1. Okay, so and then finally yeah, it is it try to see how many energy we spend to yeah, put all the charge q on the capacitor. So here we have v equals c equals qv. Here, rather than calling it q, we try to call it q prime, because we try to distinguish this dq prime with this q. So we have the q prime there. So q prime equals yeah, or actually it is like sorry, it is like v equals c v equals sorry, it should be it should be q equals cv, q prime equals cv, should be like this. Okay, so v is actually q prime over c, and then we try to plug in this one there. So we have a q prime over c dq. So this is a first order polynomial, and then we try to integrate it, becomes a second order q squared. So q prime square, and then we evaluate from 0 to q, so it becomes a q square minus 0 square, which is q square over 2c. Okay, so yeah, actually integrating q prime should be q prime square over 2. Yeah. Okay, so this is one of the expression, and another expression we will frequently use is 1/2 cv square, which means that we try to plug in q equals cv. So q square equals c square v square, and then one of the c cancel, so it becomes 1/2 cv square, which means that if we try to charge a capacitor to a voltage or the potential difference V, then it is equal to 1/2 of CV squared, which means if V is larger than the power spent is square proportionally to the square of the voltage. And if C is larger, it is linear increase. Okay, so it is equal to the work required to charge a capacitor. This energy can be associated with the capacitor E field. Okay, and this is the expression for the energy density within the capacitor. So it will be like so actually here we do not try to prove it prove this expression to be correct. We just try to verify that. Just say for paraplate capacitor, it is correct. So for paraplate capacitor, if you still remember, C equals epsilon naught A over D. If you still remember this one, and actually U equals the total U divided by the volume. The volume, yeah. Here we have a paraplate capacitor, so the volume is here. So here we have A to be the cross-section area, and then this is the distance D. So here we should have A times D is the volume between the capacitor, between the paraplate capacitor. So in this sense, we have 1/2 CV squared over A times D. Okay, so in this sense, we can also try to plug in this expression into here. So we have a 1/2 epsilon naught A over D, and then V squared, and then over A times D. So here we can cancel something. We have A and A can be cancelled. And then we all together have 1/2 epsilon naught V over D, and then quantity squared. So here, this is V between these two plates, and then this is E. So, and then we also assume that the E field is uniform for the paraplate capacitor. So here we have a V equals ED, or V over D equals E. So we have a 1/2 epsilon naught E squared. Okay, so actually we will seldom use it in individually, but actually in chapter 20, chapter 32 or 33, chapter 33, when we talk about the EM wave, we will use this expression, and also the energy density for the magnetic field. Yeah, it will be related to the energy of the EM wave. Okay, so we'll use this expression later. Okay, so here we have a sample problem. So it says, so an isolated conducting sphere with a radius r has a charge q. How much potential energy is stored in the electric field in this charge conductor? So here we have, so as much as it is a spherical conductor as a capacitor, which means that C equals 4 pi epsilon naught R. And in that sense, U equals Q squared over 2C. Just make use of this expression. So in this case, we have a Q squared, and then we just replace this C by this expression. So we all together have 8 pi epsilon naught R. So here we can just plug in all the values. So we have Q equals this number, 1.25 times 10 to the negative 9 power, and then quantity squared, over, or maybe we can just regard 1 over 4 pi epsilon naught is 8.99 times 10 to the 9th power. And then remaining, we have 2R here. So we have 2 times R is 6.85, which is 0.0685. Okay, so this number is 1.03 times 10 to the negative 7 joule. So this is the energy store in the capacitor. And then it also asks what is the energy density? So for the energy density, we know E equals K times Q over R squared. So by the Gauss law, because we just have a spherical capacitor, and then suppose we assume this is the Gaussian surface. So epsilon naught integration of E dot dA equals Q enclosed is nothing but Q, And here it is a spherical, so it is like 4 pi 4 pi r squared. 4 pi r squared times E, and then epsilon naught equals Q. So we simply get this expression. And U equals 1/2 epsilon naught E squared. So it is like, so maybe we can just write it as 1/4 pi epsilon naught, and then times Q over R squared. So this is, so we have E squared. So this whole term square, we have a Q square on the top. We also have epsilon naught, and then here we have epsilon naught squared. So we have epsilon naught on the bottom. We also have, this is square. This is square. So 4 squared is 16. Multiplied by 2 is 32. We also have pi square. So we have pi square. And then here we have a r square and then square again. So we have r to the 4th power. So finally, we can plug in the number. We have a 1.25 times 10 to minus 9th power quantity square over 32 pi square times 8.85 times 10 to minus 12, and then times this is 0.0685 to the 4th power. So this is 25.4 times 10 to minus 6 joule per meter cube. Okay, or you can write it as a 25.4 microjoule per meter cube. So okay, so okay, so if no question, I just move on. So here we talk about something strange, yeah, which is related to the dielectric. Actually, it's related to some hardcore physics, but yeah, we don't really need to really understand why but like that, but try to explain some of the hardcore physics. So it is like, here it says, if the space between the plates of the capacitor is completely filled by a dielectric material, the capacitance C in vacuum. Originally, we assume in between it is vacuum, or if it has some air inside, then yeah, these two cases are quite similar. Although, yeah, if you really check it on the book, there is a very, very tiny difference. Maybe the first significant bit after the floating point, then yeah, they'll be different. But yeah, generally we can regard the electrical property for vacuum and air will be the same. So yeah, so here, yeah, so if we fill the dielectric between the capacitor, and yeah, so the capacitance will be multiplied by the dielectric constant kappa. So this is not K, this is kappa, a Greek letter. So which is a number greater than 1. So always greater than 1. So yeah, so we assume that the dielectric constant for the vacuum is 1. Yeah, or the air is slightly larger than 1, 1.00 something like that. But for other dielectric, kappa will be always larger than 1. Okay, so this is the quick observation. So suppose we have a circuit diagram like this. Originally, we have a battery. So we have a V. We have a constant V. We don't change the battery. But if we just place some dielectric between, then we can see that there will be more charges, which means that the capacitance become larger. Or on the other hand, if we just if we just have a constant Q, which means that we try to charge the capacitance with a certain amount of charge. So let's say here we have 4 plus sign, 4 minus sign, and then we try to disconnect it. So there is no current going in or going out, which means that the charge amount cannot increase or decrease. It should remain the same. So here we try to connect a voltage meter, a voltmeter here. Then yeah, so we get a number, and then if we add some dielectric between the paraplate, okay, the voltage drop. The voltage drop means here we should have Q equals CV, and here, as much as in this case Q is constant, Q doesn't change, so this number doesn't change. This number doesn't change, and here it means that V decrease. So this one decrease, which means that C also increase. So by these two simple observation, if we just insert the dielectric inside the paraplate capacitor, then the capacitance will increase. The factor will be like the dielectric constant kappa. Okay, so here we just mentioned a bit about the atomic view, yeah, some hardcore physics. So yeah, so it is like yeah, so it relates to the dipole. So it relates to the dipole. Okay, so here here we assume there is a uniform E field pointing to the right side, and then we place some dipole in this area. So usually the dipole will not be aligned, yeah, because they will just like swinging back and forth. And actually it is hard to align all of them, because all of them will just try to swinging back and forth. Okay, so yeah, so thermal aggregation prevents complete alignment. And then here it talks about the polar dielectric. So some material are so-called dielectric. You can regard inside the material there are many dielectric dipole. So without any E field, then all the dipole will point to a different direction, arbitrary direction. And it turns out that the E field will just cancel with each other. The E field cancel with each other. So this dielectric itself will not generate a E field. So of course, if it generates E field, it will spend energy. But if there are no E field outside, then they just point to arbitrary direction, so that it does not occupy or it does not consume any power for that. Okay, so yeah, so next will be some interesting stuff. So for the non-polar dielectric, so yeah, so if there are no E field, then yeah, they point to arbitrary direction. And if we just place the dielectric inside the uniform E field, then all the dielectric will be aligned, because it will be something like yeah, suppose this is a positive side, positive plate, and this is negative plate. It will generate E field pointing to the right side. So in that sense, the plus side of the dipole of each dipole will be there will be Coulomb's force pointing to the right side for the positive charge, and for the negative charge, the Coulomb's force will point to the opposite side with the E field. So yeah, so in that case, for the dielectric, yeah, the E field will align all the dipole inside the dielectric. And interesting stuff occurs is that if all the dipole points to the same direction, so this dielectric will generate an E field pointing to the left side. And it will try to cancel a bit of the external E field. It will cancel a bit like this one. This E prime is generated by the dielectric. So inside the dielectric, the overall E field will be smaller than E0, So the dielectric is an interesting material. It is somehow like inside a classroom, although we are not in a classroom at this moment, but you can imagine, just like if we have face-to-face lecture, then yeah, if it is not during the lecture, if for example, it is slightly before the lecture, then many of the students already enter the classroom, then they may not just look at the whiteboard. Maybe they are chatting to each other, maybe they are doing something. Then they will just look at arbitrary direction, just like this one. But yeah, actually in a classroom, even though you are not chatting with each other, maybe you will try to sit on a desk, take a seat, and then generally you will try to look at the whiteboard direction, unless you are just chatting with each other. But of course during the lecture, it's just like you provide an E field to the dielectric, then all the students should be looking at the screen or the whiteboard. It is just similar to the dielectric. Okay, so next is we have more mathematical stuff about the dielectric. So here it says, when we consider the capacitor with dielectric, then we need to slightly modify the Gauss law for this case. The tiny modification is nothing but you put epsilon naught kappa rather than epsilon naught itself. So which means that for the place we have a dielectric, we just replace. Let me see. Let me see. So when dielectric is present, the Gauss law may be generalized to this one. So we just replace epsilon by kappa epsilon. And of course, it put the kappa inside the integration sign, which means that, the kappa may not be uniform. Maybe I just put multiple. For example, if we have the top plate and also the bottom plate, then maybe we try to put one of the dielectric here, and then we try to put another dielectric here. Then it just try to emphasize that for different part you should use different kappa. Placing outside will be a bit strange because you cannot distinguish. But if you place it inside the integration size, then you should be cautious about, if I just integration from here to here, then for this part I should use maybe just say a kappa 1 for here, kappa 2 for here. Then just keep in mind you have a factor of kappa. Okay, so actually in this textbook we don't really talk about displacement, but maybe in electromagnetism class for ECE student, then you may face this so-called displacement of the electric displacement. So which is like D equals epsilon naught times kappa times E, so something like this. But if you are not ECE student, you can just forget this part. Okay, so so here let's take a look at a sample problem 25.05. So it says a paraplate capacitor whose capacitance C is charged by a battery to a potential V between its plates the charging battery is now disconnected and porcelain slab is slipped between the plate. What is the potential energy of the capacitor before the slab is insert? Before. So before is just simple. So which is nothing but a VI equals 1/2 CV squared. So C is the original C because it mentioned it is before the slab is insert. So so we have all the numbers. We have 1/2 times this is 13.5 pico is 10 to negative 12, and then times V is 12.5 square. So this is 1.055 times 10 to negative 9 joule. Okay, so this is the answer for part A, so which is very trivial. And then next, what is the potential energy of the capacitor slab device after the slab is insert? After it is insert. So after it is insert, so we should have a C prime equals kappa times C. And here we have the kappa to be 6.5. So it should be times 13.5, which is maybe we don't need this number yet. So maybe we just plug in this C prime into the expression we like to. So UF, maybe we call this, we have a U initial and then U final will be 1/2. So here it says the battery is now disconnected, which means that the variable doesn't change, is actually Q doesn't change. Q does not change. Q does not change because it's mentioned that the charging battery is now disconnected. So there is nothing more. There cannot be any current going in or going out, which means that at the very beginning we have a capacitor. We try to charge the capacitor with a battery. So this is the second step. So in this case, it becomes 12.5 volts here. So there will be some charge plus Q and negative Q. And then here, we try to replace it. Remove the battery. And then the next step is to insert the slab. And here, Q does not change, doesn't change. Does not change. However, this voltage will change. This voltage will reduces because this capacitor becomes larger because the Q equals CV. So this becomes larger, this becomes smaller. Okay, so in this sense, we should use actually, as much as we know, Q doesn't change. So we should use Q squared over 2C prime. Q squared over 2C prime. Yeah, so it will be like Q. Q doesn't change. So Q equals CV, which is 13.5 times 10 to minus 12 should be the original one. And then times the original voltage, which is 12.5, and then whole square. So this is the original charge, and the original charge doesn't change. So don't try to mix up with this C prime. But here we should use C prime because this is the final capacitance. So times kappa is 6.5 times 13.5 times 10 to minus 12, like this. Okay, so try to bear in mind this one is C prime. This is only C, because otherwise, if you use C prime, you should also use B prime. But actually, C prime becomes larger and V primes become larger. So we don't have C prime and V prime either. And actually, this is nothing but C times V. So we use the original C and original V. And then finally, yeah, so this number is nothing but 1.62 times 10 to minus 10 joule. Okay, so when you just check this number with this one, so this is larger than this one. So which means that some energy loss. So yeah, so it means that W equals UI minus UF equals 1.005. Of course, this is not asked by the question, but yeah, so but we just try to calculate this thing. So this is the origin of 10 to the negative minus 9 minus 1.62 times 10 to minus 10. So this is 8.93 times 10 to minus 10 joule. Okay, so just as what I've mentioned is that for the original case, it is like this is plus Q. This is 12.5 volt, and then we don't have the dielectric. So if we just place the dielectric, the energy stored in the capacitance becomes smaller because some energy are absorbed by the dielectric. I just mentioned that the dielectric is like if you provide the energy, which means that you have a external E field for the dielectric, then it will generate E field on the opposite direction, which cancel part of the external E field. So in this case, the dielectric need to absorb some of the energy from the outside, from here. It should absorb some of the energy here, so that it's stored inside the energy go inside the dielectric. So from the outside, you can just observe the energy in the capacitor is like this. Some of the energy are actually inside, but you cannot observe. The energy there is to let the dipole align to a direction. Okay. So next we have another sample problem. Okay. Okay. So here it says a parallel plate capacitor of plate area A and plate separation D. Okay, so we have the cross-section area A, and then this is the plate separation D. Okay, a potential difference V0 is applied between the plates. Okay, so there are potential difference V0. And then the battery is then disconnected. So just similar to the previous case. And here we try to insert a dielectric step of thickness B, so not D anymore. So this B is shorter than D, so there are some gap between the dielectric and the parallel plate. It doesn't necessary to know how long is this part and also this part. Yeah, it doesn't really matter. We only care about that this plate is parallel to the original capacitor is enough. Okay, so it says dielectric slab of thickness B and dielectric constant kappa is placed between the plates. assume A, D, V0, B, and kappa to be these values. So what is the capacitance Z0 before the dielectric step is insert? So before. So C0 is nothing but epsilon naught times A over D. So because it is a Paraplate capacitor, so we can simply apply this formula. So this is 8.85 times 10 to minus 12, and then times A is this one. But actually, we should convert it to meter square. So 1 centimeter, 1 meter is 100 centimeter, which is 10 to the 10 square. So here it is a cm square, so it should be like 115 times 10 to the negative 4th power meter square. And then, yeah. And then all over this one is a 0.0124. Okay, and this number is 8.21 times 10 to minus 12 of farad. I think I forgot to introduce the SI unit for the capacitance. So the SI unit for the capacitance is farad. Maybe I should introduce it before. Slightly around, let's see, should be somewhere here. So the SI unit for capacitor is farad. Farad. So we use a capital F to represent farad. So first, it should be related to Faraday, but yeah, here is called farad. Okay, so here we have this is C0. And then for the next one, what free charges appear on the plate? So yeah, for this case, it is still before the slab is insert. So here we have a Q0 equals C0 times V0. So we just plug in the number 8.21 times 10 to minus 12, and then times V0 is this one, 85.5. So this is nothing but 7.02 times 10 to negative 10 power Coulomb. Okay, so actually you need to slightly remember the SI unit. So for the C, it is C is farad. So this is the variable. This is variable. This is SI unit. This is SI unit. So for Q is C. Q is Coulomb, and then C is farad. Yeah. Okay, so part C, what is the electric field in the gap between the plate and the dielectric slab? Okay, so here we would need to apply the Gauss law. Okay, so for between the plate and the dielectric slab, which means that we try to conserve the E field here or here. So in this case, we try to apply the Gauss law for Gaussian surface 1, GS1. So in this case, let me try to write out the Gauss law. So epsilon naught times integration of E dot dA equals Q enclosed. Okay, so here, for this one, we don't have any dielectric inside this Gaussian surface. So we don't have copper here for this part. And of course, for this one, it is like a rectangle. So this one is inside the conductor. We don't have an E field. And here, the E field are also perpendicular. Perpendicular to the dA. So only this side contribute to the net flux. So in this case, we have a E equals, actually Q enclosed is plus Q. So we have Q over epsilon naught times A. So because E is uniform over this surface area, so epsilon naught times A, or maybe we can write it as epsilon naught times E times A equals Q, and then we get this expression. So in this case, we have actually this Q is actually Q0. It's actually Q0. It's actually Q0 there, or maybe or maybe I can just write this is Q. This is Q, or I just put this is just put Q here. I just put Q here. So yeah. Then we will not introduce too much variables. So this Q is Q. Yeah. So this Q is actually this one, which is 7.02 times 10 to minus 10 over 8.85 times 10 to minus 12 times this is 115 times 10 to minus 4th power. So this number is actually 6,900 volts per meter. Okay, so this is one of the possible SI unit for the E field, or you can also use N over C. Both of them are correct. Okay, so this is the E field in this region or in this region. And then here we try to consider E1 inside the dielectric slab. So just now this is E, this is E, and this will be E1. This will be E1. So here we apply Gauss law for the Gaussian surface 2. So for this one, we only enclose the negative charge. So which means that epsilon naught integration of kappa. Yeah, because for this part we have for this surface is actually inside the dielectric. So we have kappa E1 E1 dA equals negative Q. Yeah, because it only encloses the negative Q in this region. So in this case, and actually I think there should be another negative sign here, because for this surface, E1 is pointing downward. However, DA is pointing upward here. So E1 and DA point to opposite direction. So we have another negative sign. And then finally cancel this negative sign. So all the other stuff are positive. So in that case, or maybe we can just put here, we don't have the negative sign yet, because we still have the dot product here. But for the next step, we should have a negative epsilon naught kappa E1A equals negative Q, and then the two negative signs cancel each other. And then we can get E1 to be Q over epsilon naught kappa A. So when we plug in the number, it is 702 times 10 to minus 10 over 8.85 times 10 to minus 12, and then times kappa is 2.61, and then times 115 times 10 to minus 4th power. Okay, so this number will be 2640 volts per meter. Okay, of course, it is smaller than the E itself. Yeah, because we have a dielectric. So it cancels some of the E field, absorbs some of the power. So the E field will be weaker there. Okay, so next, what is the potential difference V between the plate after the step has been introduced? So here we have a V equals integration of a EDS from negative to positive. So we try to integrate from here to here. So in this case, as much as E is uniform in this region, and also in this region individually, so it is like just multiply and add together. So it is like E times E1 times B, because inside this region, the height is B, and then the magnitude is E1, and then outside part is E, and then the height should be D minus B. So this number will be 2640 times B is this one, 0.078 plus 6,900, and then times this is 0.0124 minus 0.0078. So this number will be between the, actually it should be smaller than this one. It should be smaller than this one. And this number is 52.3 volt. 52.3 volt. And so it asks what is the capacitance with the step in place between the plate of the capacitor. So finally, we can simply calculate that C, the final C is Q0 over V. Yeah, we get the new V. So it is nothing but 702 times 10 to minus 12 over V is 52.3. 52.3. So this number is 13.4 picofarad. 13.4 picofarad. Originally, C0 is 8 picofarad, 8.21 picofarad. 8.21 picofarad. Sorry. So now after inserting the dielectric slab, but of course this one is not as high as the plate distance, but still the capacitance increased not by 2.61 times, but yeah, at least it is larger. So it is actually a weighted average between this one and this one. This one, yeah, for this part, it is still the original capacitance, but this part, it becomes larger. So on average, it becomes a larger capacitor. And this conclude this chapter.